Now let's look at these types of metamorphic rocks. So we're going to break them down into two fundamental groups. The foliated rocks, which are going to have that preferred direction. Usually there's some differential stress involved. And also the minerals will help us identify what happens, because we're going to differentiate between the different, like schist and gneiss. Usually the minerals will be different because higher temperature minerals will form in the gneiss, whereas lower temperature minerals will form in the schist, right? And for the non-foliated rocks, since they do not have that preferred direction, we're going to mostly just look at the minerals to help us identify the source area and how these rocks formed. So remember, for foliated rocks, folium is Greek for leaf, right? And you're going to get these parallel surfaces or layers. And again, we're going to distinguish these metamorphic rocks based on the mineral composition, how coarse or fine the rock is, and then the type of metamorphism, right? Whether it's those bandings or that mineral alignment, or in some cases you can't even see minerals, so you just have this slaty cleavage, and that's what this one over here is. So slate is the first metamorphic rock, and it does have this slaty cleavage, right? So so think about just like cleavage. There's these parallel fractures that occur in the rock, and really the slate is going to be composed primarily of clay minerals. In fact, primarily it's a mineral chlorite, because slate usually, in fact, we'll say here, I'm going to use a word here, low grade. So slate usually forms at low grade, and remember, grade is an intensity of metamorphism, and it really reflects temperature. So usually slate is going to be metamorphosed at a relatively low temperature and produce these clay minerals, right? And the protolith of slate is going to be a shale or a mudstone, right? And usually what happens to grow these clay minerals, we're going to have that pressure solution. Pressure solution is going to grow these clay metamorphic minerals. Chlorite is a good example. Now phyllite, again, this is going to be also low grade and a relatively low temperature. A little bit warmer, maybe higher grade than slate, but not very much, still in this low grade region. And the thing about this one is that we're going to have the neocrystallization of white mica. So we get this sleek sheen, this kind of shininess. In fact, they call it a luster, phylitic luster. So phyllite and slate look very similar, except phyllite will have this shininess, this sheen to them, right? So that's one thing we'll look for. Then another rock your book mentions here is metaconglomerate, and I talked about this a little bit. And this is where you take a conglomerate, a protolith, and you're going to either bring it to higher temperatures and pressures to allow some pressure solution to occur and plastic deformation to stretch out those pebbles. Sometimes you call it a stretched pebble conglomerate, but usually we just call it a metaconglomerate. Now, schist is a rock now we're going to medium to coarse grain, so we change the grain size and we get this schistosity. And schistosity here refers to a preferred orientation of large mica flakes, right? So we're seeing again that neocrystallization of mica flakes, and the minerals define the preferred orientation. Another thing about schist is we're going to have something here called medium grade. So in other words, we're going to be hotter. So we've taken the rock now to a higher temperature than the phyllite or the slate. In fact, you can take that phyllite and slate, and if you heat it up to higher temperatures, you can make schist out of it. So sometimes people refer to the protolith as schist. Well, the protolith of schist would be either slate or phyllite, right? Because that's a little bit lower grade. So we're moving prograde or toward this higher metamorphic grade. Now for gneiss, well, the protolith of gneiss could be a schist. I just take schist to a higher temperature. So this is going to be high grade here. So this is forming at the higher metamorphic intensity, higher metamorphic grade. And the result is that we get this banding, right? So the gneissic banding, light and dark layers. And so how does this form? Well, maybe you're metamorphosing a section of shale and sandstones. Well, the sandstones turns into quartzites. Shale turns into these schistosity layers within there. So you got some layering going there, or maybe you can get plastic flow and shearing that smears out the layers. And then your book talks about this idea of metamorphic differentiation, where chemical reactions can actually move around chemical elements into preferred light and dark banding, right? But the key thing about the gneiss is you're going to get the light and dark banding, the gneissic banding. And finally, the last rock here is this Migmatite. Migmatite is a relatively strange rock. I call it a hybrid rock because it got so hot. In fact, let's see here we'll add the highest grade. Because once I go any higher in temperature, I'm going to melt it and produce an igneous rock. So this, in fact, part of this rock began to melt, producing felsic magma or quartz. Usually you get quartz that develops here. And the quartz is magmatic, so it's igneous, but the remainder part of the rock is metamorphic. So this rock is hybrid, part metamorphic, part igneous, right? And so we get to that highest metamorphic grade. Now, looking at the non-foliated rocks, we're going to recrystallize the minerals, right? So basically, we're going to get some coarse minerals, some bigger minerals. A good example is marble. Marble is a beautiful rock because it has nice big crystals of calcite. Well, the protolith of marble is limestone, which is a fine-grained calcium carbonate, right? Other things that can happen is you can get some new metamorphic minerals that will grow, right? So again, the non-foliated rocks have no foliation, right? So it means that there was no compression or shear going on, no differential stress. So they're primarily, maybe they're just forming from hot fluids moving through the rock. Maybe burial metamorphism is occurring on these, where you're getting more of that confining pressure, right? Confining stress rather than the differential stress. There's three important rocks that I want you to know. In fact, there's a fourth one. We'll talk about the fourth one as well. So these include hornfels, quartzite, and marble. So hornfels is a general fine-grained metamorphic rock. It formed by this process called contact metamorphism, which means some magma intruded and burned the wall rocks. Right? So you can think of hornfels as, in fact, I have here burned wall rock. Right, so the rock adjacent to the magma chamber, adjacent to the intrusion, got burned, and so usually it's at pretty high grade because of metamorphic. So in fact, we'll have high grade, high to medium grade, because that magma intruding is already at 800, 900, 1,000 degrees centigrade. So it's going to really burn these rocks adjacent to that intrusion. Quartzite is another a non-foliated rock that has a protolith of a quartz sandstone, right? And so you get recrystallization of these quartz grains where they become interlocking. So you lose the pore spaces. Those pore spaces disappear, and the rock, it tends to get this welded structure. And so when you try to break quartzite, it breaks through the sand grains rather than in between the sand grains or around the sand grains. Another way you can determine quartzites or differentiate quartzites from sandstones is that quartzites you will not be able to rub the sand grains off because they're welded together. Whereas in a sandstone, you can rub the grains off. Now, I've mentioned marble a little bit, so the protolith is a limestone, and it's really this recrystallization process. Let's look at the PowerPoint here, right? So just to kind of review some of the things we've talked about. So remember, metamorphism involves changes in mineralogy. That's one of the things. So either the coarsening or these new metamorphic minerals are forming, right? And if we kind of keep going here, so the texture can also change. Here we have fossils and calcite and a limestone and a protolith, and then now we see the recrystallization where these grains are now interlocking. So there's a change in the texture. So recrystallization, same idea here. Here we have tiny broken particles, and like in a sandstone, and then now they're interlocking like in a quartzite. And so that's a good example of recrystallization. In the neocrystallization, here we have clay and quartz, and as metamorphic reactions occur, we can crystallize new minerals like white mica, garnets in here, so we can get this neocrystallization that develops. And then that pressure solution, because there's a differential stress in going on the side of this, we're going to dissolve material off the end of these and move them to other parts of the rock here. So we get this pressure solution and we get these elliptical grains rather than the spherical grains. Plastic deformation, right, where we're going to, again, where the rock warms up enough where we can stretch these pebbles and make them more elongate. So we talked about these agents of metamorphism, right? The heat, the pressure, the compression, the hydrothermal fluids. And so this just depicts compression, right? So this is really a differential stress because there's greater stress in this direction than in this direction, right? So it's going to lead to that foliation, that preferred orientation or fabric. And then here's another idea where we have stress occurring horizontally here. We get compression. If we pull apart, we get tension. And then this depicts the shearing motion where one block is sliding by another block here. Shear motion there that can stretch some of these metamorphic minerals, rotate the grains into that plane of foliation. And then here's a little micrograph looking at a microscope image of foliated rock. So all these platy metamorphic minerals are in this plane of foliation. So one thing you should see is that the plane of foliation will always be perpendicular to the zone of compression or the differential stress. And so just to give you an idea of what inequate minerals are, they're either platy or flat, or they have this long aspect ratio here. Now, foliation. So this is a gneiss, so you get the banding right here. So again, this preferred direction in the rock. And non-foliated rocks, well, this marble, you don't see that foliation. Now, how do you get the foliation? Well, this first one here is slate, right? So slate has this slaty cleavage, and you can see they're kind of showing that you can take a chisel and break off these slates. In fact, many slates are used for slate roofs, right? And then phyllite, so you can see that phylitic sheen, that phylitic luster. And then this one here shows a stretched pebble conglomerate. And then this one here is showing the schist. So the first thing you see with a schist is that you see the white mica minerals, right? You see those minerals all in the plane of foliation, right? So that's what we call this schistosity. And then now the banding, right? So the light and dark banding, well, that's the metamorphic gneiss. So the distinct compositional bands, usually you get the quartz and feldspar in the light colored bands, and the mafic minerals in the dark colored bands. So remember, amphibole is a hornblende, dark mineral. And then how does this banding occur? So here we have maybe a rock with some mafic components in it, some mafic minerals. So the mafic minerals get stretched out along with the rest of the rock, and the mafic minerals seem to either differentiate into these darker layers, right? So you get this compositional banding with shearing. Chemical reactions occurring here, moving felsic minerals into the light colored bands, moving mafic minerals into the dark colored bands. So that's that metamorphic differentiation. Now, for the non-foliated rocks, one of the ones we talked about is the quartzite. So your quartzite, you can sort of see a sugary, grainy texture, but again, in a sandstone, you'd be able to rub the grains off. In the quartzite, you will not be able to rub the grains off. And then marble, remember the protolith of marble is limestone.